In this video, we're going to be taking a look at two fluid problems where we're going to be using Bernoulli's equation. And we have one pipe going from a larger opening to a smaller one, and a second one over here that goes from opening 1 down to opening 2 at a lower level, and we do not know the area and the pressure. So let's go ahead and take a look at our first example here. Now, we have the water flowing at 4 meters per second, and as the opening shrinks, the velocity is definitely going to increase. So we're going to go ahead and use the continuity equation where we have the area and the velocity of our first opening equal to the area times the velocity of our second opening. So we have an area of 2 meters square for that first opening, and the water is flowing at 4 meters per second. And then for our second one, the opening shrinks down, and we have an unknown velocity at our second opening. And we have 2 times 4, which is 8. And then we're going to go ahead and divide both sides by 0.5 to cancel that out and isolate our V2. And then we have a velocity of 16 meters per second, which makes sense because we're looking for the velocity to increase as the area decreases. Now, that wasn't asked of us in the original problem, but I can already foresee that I'm going to need that velocity a little bit later when I use Bernoulli's equation. Now, when I use Bernoulli's equation, we are taking a look at P1 plus rho g h1 plus 1/2 rho v1 squared equal to P2 plus rho g h2 plus 1/2 rho v2 squared, which is combining all the static and dynamic pressure from point 1 and then setting that equal to the static and dynamic pressure of point 2. So we know a couple values, and we can also do a little bit of cancellations as well. So we don't have any change in height. It's all at the same level. So we don't need to include any H's. Everything is at height 0. So that is a non-factor. And then we have the pressure for our first opening as 200,000 pascals. And then plus 1/2 rho v1 squared. So 1/2, and the rho, the density of water, is a constant of 1,000 kilograms per meter cubed. And we know that velocity is 4. So we have everything on our left side, and P2 is our main unknown variable. So of course we don't have that quite yet. 1/2, same rho, 1,000 for water. And then we just got that V2 a little bit earlier, so we got 16 squared right over here. So if I go ahead and multiply out these numbers here, that comes out to 8,000. Which leaves us with 2,800 pascals over here. And then if we combine all these values over here, find the product, we get 128,000 pascals right there. And we are just about done. We just need to subtract this from both sides. And then we have our final P2 of 80,000 pascals. So overall, because of the change in area, the increase in velocity, the pressure is going to drop from 200,000 to 80,000 pascals. So two things we needed to utilize, which are fairly common, is our continuity equation in purple over here, and then using Bernoulli's equation, this red version over here, except we got to cross out a couple things because we didn't have any delta H or change in our vertical position of each of those openings. Okay, so let's go ahead and clear our work for the bottom screen, and then we'll get to a slightly more difficult problem over here where we do have some changes in our vertical positions. All right, so we are completely done with this problem. So we'll put a big check over here. And now we're focusing on our second problem. So it looks like we're going to have a similar approach. We have a lot of values for the first opening over here, and then the second opening over here. We have a velocity, and then that's about it. So I want the area, and then we eventually want the pressure. So let's go ahead and find that area first. So we're going to use A1 times V1, which is the 3 and 15 are known variables from over here. And let's set that equal to the A2 unknown times our V2. And then 3 times 15 is 45. Oh, that is not 45. 45 equal to A2 times 5. Go ahead and divide both sides by 5. And then our area comes out to 9 meters squared. And then we have our first answer. We got our area. Now we're going to go ahead and utilize Bernoulli's equation once again, where we have the pressure plus rho GH1 plus 1/2 rho V1 squared equals P2 plus rho GH2 plus 1/2 rho V squared. Okay, so what we can do is we have 10, which is our delta Y. It shows the height of the center of opening 1, and then the height as the center of opening 2. And we can go ahead and call this our base of 0 meters, which would make this 10 meters. So we can go ahead and drop this one off because we're calling our H2 0, but then we do have an H1 this time. So let's go ahead and plug in some of our values. Let's go ahead and separate this. We have a P1 of 200,000 pascals plus rho GH. Rho is 1,000 because we're dealing with water. So it's the constant of 1,000 kilograms over meters cubed times our constant of G, which is always 9.8, and our H1 we just said is 10. Okay, so that's that. And then I'm kind of sliding over pretty far to the right over here. So plus 1/2 rho. And then our V is 15. And then we're going to go ahead and square that value. Okay, so if we find the product of our 1/2 1,015 squared and our 1,009.8 times 10 and add that to our 200,000, that comes out to 410,500 pascal. So that takes care of the whole left side of our formula that I boxed in green over here. Now let's go ahead and work on the right side of our formula where we have P2, our main unknown, plus 1/2 rho 1,000 for water again, and then our velocity is 5 for opening 2. And then the product of these is going to give us 12,500 pascals, and we are just about done. We just have to do a little bit of subtraction to cancel this out and get our P2 all by itself, and that will give us 398. thousand pascals for our final P2 pressure. Okay, so for this one, just one of the main differences was that this one we didn't have the area, so we had to use the continuity formula. Just a quick little algebraic step, dividing both sides by 5 to get 9 meters squared, and then utilizing Bernoulli's equation again, identifying our heights initially. So this is our baseline height of 0, and then we have a height of 10 up here for number 1. So we have a little bit more going on numerically. Plugged in all the numbers for our left side to find a grand total of 410,500 pascals on the left side, and then plugged everything on the right, did a little bit of algebra once again to find our final P2. So I hope that was helpful and helping you set up some Bernoulli's equation problems. Thank you for watching and listening.